So in this section, the textbook is going to assume that you are familiar with all the different parent functions from Algebra 2. And I also assume that when you walk in the door. You're familiar with quadratics, absolute values, square roots, cubic functions, that type of thing. One that you are not familiar with that we want to talk about is the greatest integer function, which is an example of something called a step function. So just real quickly, in general terms, a step function in mathematics is a function that resembles steps or stairs. Now, I would guess when most people, if I said, draw me a set of stairs, you would draw something that looks like this. But a mathematical step function can't look like that because it won't pass the vertical line test and actually be a function. So the step functions that we talk about don't have this vertical rise piece. And so our steps really look like floating stairs, I would refer to them. Okay, so they like step up, they can step down, and that's a step function. Now, one issue with the step functions is sometimes these steps, you know, they normally would be connected with a vertical line, but I can't have 2 points of the same vertical line, so I'm going to have a lot of open and closed circles. Okay? So like if this circle was closed right here, then this first point on my next step would have to be open if there was no gap between the axes. So you're going to see that with our greatest integer function. There can be a series of open and closed. And that's to preserve function. So here's the greatest integer function and what the greatest integer function means. The greatest integer function is notated by what looks like double absolute values, or sometimes it looks like double brackets, like when I draw the greatest integer function, you're going to see me write it like this. They're the same thing, same notation. So both means greatest integer. And the greatest integer function is asking you, like, when you put in an x value, find the greatest integer that is less than or equal to x. And we'll practice this here in just a moment. While you're jotting that down, can you guys just shout out, what are some examples of integers? 1, 8. No. Negative 3. 12. 5. 25.
Anything without a decimal.
Anything without a decimal. 0? Yeah. Yeah. Anything without any like decimal fraction piece to it, that's going to be an integer. I call integers unofficially nice numbers. You know, when you ask your math teachers, my answer going to come out to a nice number, you mean an integer. Okay, something without a decimal or a fraction. Okay, so we're selecting only integers, okay, when we use the greatest integer function. So we're going to do some practice with evaluating. So I've got some function notation over here. We'll practice evaluating, and then we'll graph. We're going to do f of 0, f of 0.5, f of 1, f of 1.2, and f of 2. Okay, if I put 0 into the greatest integer function, I would read that as selecting the greatest integer, nice number, that is less than or equal to 0. That would be 0. So this is my x, and this is my y, and 0, 0 is a point on my graph. For f of 0.5, the greatest integer of 0.5, is asking me to select the greatest integer, oops, forgot my 0.5. The greatest integer that is less than or equal to 0.5. 0 is the closest integer to 0.5 that's not more than 0.5. Does that make sense? Okay. So 0.50 is also on my graph. There's my 1 mark. If I were to do the greatest integer of 1, what's the greatest integer for 1? 1. Okay, the highest integer that's less than or equal to 1 is also 1. So when you get to 1, you're going to jump up. That's going to be a step up. Think about that step function and think about all these points in between 0 and 1. If they were put into the greatest integer function like 0.1, 0.2, 0.33333, 0.75, 0.999, what are they all going to give you in the greatest integer function? 0.1, 0.2, 0.3. They won't go up to 1. They'll go down to 0. So there's a step in between 0 and 1 where everything goes back to 0. Okay? When you get to 1, you're not 0 anymore, you jump up to 1. So you have a closed circle and with an open circle. Now when you do things that are more than 1 but not 2, they're always going to give you what for the greatest integer? 1. So I could plot 1.21. And as soon as I get to 2, my greatest integer function is going to give me, greatest integer of 2 is 2. I already have 2 up there. So 2, 2 is going to be a closed circle. So all this piece right here, from 1 to 2, all those decimals, 1.1, 1.2, 1.3, 1.99, they're all going to give me greatest integer of 1. And when I get to 2, then I jump up. You see how those steps are being created? And then you can just continue the pattern. Okay, so if you want to draw a few more steps, add one down here for -1. Down to greatest integer function. Does anybody have any questions that I can clear up about greatest integer function? Yes. The open circle?
Yeah.
You need the open circle, yes. So I know I saw some people on the pink sheet, like they use either, I don't know what it looks like in the back of the textbook, either use the textbook or Google, and like sometimes you'll see just like little horizontal lines for a step function, but we want to mark that open circle saying that at all of these locations, we will pass the vertical line test. Nathan?
Pink sheet for greatest integer function, and I can't seem to figure out how you would write the range in the notation.
So the only kind of outputs that you get are what types of numbers? Integers. So if for range, you just want to write the set of integers, I think that's okay in this case. We don't know how to write that in interval notation right now, so we can just say the set of integers. And also on that one, since we're talking about the pink sheet right now, thank you, Mason, go ahead and say like, you don't have to do x-intercept. Write that in your box for intercept. You don't have to do x-intercept. Why am I not making you do x-intercept? There's infinitely many between 0 and 1. So I'm not going to have to write them all down. So you don't have to do the x-intercept. Could you still do the y-intercept? Yeah, there's one point that crosses the y-axis, 0, 0. So you could still list that.
What was the parent graph?
This. We could do things to the greatest integer function like, add 4, and then it would go up 4. So then this step that would normally be right here would be up 4. But this is the parent graph where the first step is at 0 from the origin.
Is the domain negative infinity?
Yes. because we have them connecting at those locations. Open close. Good. Now, also in reference to the pink sheet, I said as I was coming around, like, I'm not going to check your pink sheet. I'm going to leave that up to you. You're responsible for that information. The answer key is posted on my website. So I uploaded the file, or a link to the file for the pink sheet. So look at it, double check it. If you have questions, like, I don't know how to do domain arrays from this, certainly ask those questions, but check the answer key online. You can put a little note there for yourself if you want. Okay, next up, we're going to do some notes for parent functions and transformations. I'm going to give you a few minutes with your small groups to try to fill out this top part of this worksheet, which is writing equation for y equals x squared if we transform it some way. So this is like, what do you remember from algebra 2? Okay, so see what your groups can come up with. I'll put the answers up on the board.
Actually, I can
check
tell you
what
that.
you agree.
I know this is the actual stuff right now.
Okay, so you and your group should be working on A through F, the top part. Okay. Do Zoom, and 6. That'll get you to the standard window, -10 to 10.
Okay.
So it was probably zoomed out so far that you couldn't even see it or something like that. So if you can't see something, always check your Zoom.
How'd you get X from that? Because it's just a right 7 and it's the opposite when it's from the
Oh, and she just made one now. Wait, is vertical or
No.
is that what you
Oh yeah. So like watching.
Oh wait, no, I didn't give you a factor, so you could pick any number that you think will vertically stretch it.
Okay.
How about that?
2.
Sam, Willard, are you needing a pink sheet? I have videos posted online. Yeah, I think that I've handed out. I would agree with that.
Well, like transformations are those are they're fun. Yeah, they're really enjoyable.
I like what you guys are saying. That's nice.
Okay. You know how everybody told me into geometry was like prints are terrible. Like,
Oh my gosh,
the easiest thing ever.
No, I believe you're going to be so bad.
Like, there's no your whole
Okay, let's check your answers so far. See what you think in your group. Even if you didn't finish, do you agree with what you have so far? To shift right, it should be quantity x minus 7 squared. To shift left, quantity x plus 3 squared. Remember having those discussions where when you shift left and right, it's like the opposite of what you think it is? Because minus 7 actually goes right. Okay. To do up and down, you just do that outside of the function, so add or subtract, whatever you want to do, and those things do what you think they'll do. So plus goes up and minus goes down. To vertically stretch, I didn't tell you what factor. You can have any number greater than 1. So you could have y equals 3x squared, y equals 10x squared. Any number greater than 1 is going to be a vertical stretch, and reflect over the x-axis is y equals negative x squared. How'd you do on those? Pretty good?
We even put 2.
Oh, nice. Yeah, that's a common one. Okay, So now we're gonna fill out the bottom half there. And do you remember talking about like A's, H, and K as the transformations? Okay, so you probably wrote down like the transformations X plus H, X minus H, left, right. We're gonna write our transformations in function notation, because we're in pre-calculus, so that's something we can do. Remember, function notation is really f of x, so we're gonna be putting the shifts with f of x. Now, I gave you an example that had x squared, but it could have been absolute value of x, or x cubed, or square root of x. We're just going to leave it in function notation. To translate left, it should be f of x plus c in parentheses. To translate right, f of x minus. Translate up. This time, leave f of x alone and just add c on the back. And so it's what we're seeing in the actual functions, x squared, absolute value, but in function notation. We don't actually know what function it is. And translate down, f of x minus c. To reflect in the x-axis, you want to put the negative outside of the function. You want to make the whole function negative. That's going to change the y value and reflect it over the x-axis. If you want to reflect in the y-axis, put the negative inside with x. Are we okay with my notation so far? To do the stretches, vertical stretch is probably the most common stretch, and that's the one where you multiply the y value by something. So we would write it as c times f of x versus a horizontal stretch or shrink is going to be f of cx. So you put that multiplication factor inside with x. Now, that asks the second question, what kind of values will stretch or shrink? To vertically stretch, the absolute value of c should be greater than 1. To vertically shrink, the absolute value of c will be less than 1, but greater than 0. And the reason I use absolute value there is because if it was negative, that negative would be part of the reflection. It would not be part of the stretch or the shrink. So you really are only looking at the numerical value, not the sign. And then horizontal is probably the one that algebra 2 students don't like. Okay, it's the weirdest one, I think, for a lot of us. And the way I remember horizontal stretches, it's just like left and right. It's the opposite of what you think. So to horizontally stretch something, normally you'd think use a bigger number. It's going to be those numbers that are between 0 and 1. It's going to be fractions that horizontally stretch the graph. And to horizontally shrink the graph, then you choose absolute values that are greater than 1. And so it's flip-flop from vertical stretch. And those things would happen inside with x. So really quickly, I'm going to run through an example of what that might look like on the homework assignment so that like you're comfortable with the directions. And this piece right here where we do the function notation is going to be probably like the newest piece, but it might be covered in the new Algebra 2 textbook. So this is an example of what the homework might ask you to do. You get a function, g of x equals 7 minus x squared. And then we have to do these 4 things for that function. So take a quick minute in your small groups and see if you could talk about A through C. What would you do? What's the parent function? What are the transformations? And how would you go about graphing it? I'll give you just a quick minute to chat. 7 minus x squared.
what?
Does it identify the paragraph?
What's our paragraph?
Quadratic.
Quadratic. When it says parent function, then we want to write it in function notation. So f of x equals x squared. And that's its parent function. What are the transformations? Reflect in the y-axis and up 7. Oh, reflect in the x-axis. The negative is in front of the x squared. So that's a reflection in the x-axis. And then it's going to go up 7. And you can use those transformations and your knowledge of the parent graph to help graph it. So I would go up 7. Sorry, it's not calibrated over here. And put a point for my vertex at 0, 7. The vertex moved up 7. And then what will the negative do? Make the parabola open down. Okay, so imagine that's happening at the y-axis. I'm sorry. You went up 7 and then you flipped it. And then D is new. Use function notation. So remember, function notation is f of x, right? So it doesn't mean use x squared. It means write only with f of x the things that you want to do to it. You want to move it up 7 and reflect it in the x-axis. So reflect in the x-axis would be negative f of x, and up 7 would be plus 7. That's it. That's all function notation is. I should not, when you write function notation, I should not know, unless I know the parent graph, what function it is. So you're not going to see like absolute value bars or squares or square roots or anything like that. Now, you have a homework assignment on the gold sheet. We'll go over questions at the beginning of class tomorrow. We have less to do tomorrow than we did today, so today's kind of a whirlwind of information. I am handing out the problem set to you in case you want to get started. When is your problem set due? We got their gold sheet. When's the problem set due? Thursday. So if you want to write at the top of this is due Thursday. When is your quiz correction due? Friday. If you're confused on the gold sheet by those reflection questions, remember those are the quiz corrections. So you could cross that off if you wanted to. Now, I'll say more about the problem set tomorrow because I'm running low on time. But if you get started on it tonight, here's what I would say. Make sure you do the right problem, like Miss Cronky, doing the wrong problem. Read the directions, show your work. Those would be like my basic pieces of knowledge to you about the problem. And I'll give you more tips and tricks tomorrow about how to do the best problems.
Like up there too, like I can see through.
This is due Friday. No, this is due Thursday. The quiz correction is due Friday. Both go in the formative folder.